Hey everyone, today we're going to be talking about the graph of a function. Before we begin, we're going to start with the do now, just a little algebra to get ourselves warmed up. So if we consider the function f of x equals x plus 1 over x plus 2, is the point 1/2 on the graph of f? In other words, if we were to graph that function in our calculator, would we see the point 1/2 on that graph? Well, how could we figure this out? Well, basically, if we plug in 1, we should get a half. So that's exactly what I'm going to do. I'm going to go ahead and plug in 1. And I get 2/3. So no, this actually means the point 1 2/3 is on the graph. So no, that point is not on the graph. If x equals 2, what is f of x and what point is on that graph? So if x is 2, f of 2 is going to be 3/4. So the point 2 3/4 is on that graph if we were to sketch this function. If f of x equals 2, what is x and what point is on the graph of f? In this case, we're looking to see what x value gives us an answer of 2. So to solve this, we're going to have to cross multiply. And I get, if I subtract that, x is going to equal 1 minus 4 is -3. So basically, we have to plug in -3 to get 2. So our point would be -3, 2. And what are the x-intercepts of the graph? Remember, x-intercepts means we're going to set y equal to 0. So we're going to set this function equal to 0. Again, we have to cross multiply. So I get x plus 1 equals 0 times x plus 2 is just 0. And our x-intercept is -1. Or the ordered pair, -1, 0. That would be the actual point. So just a little algebra warm-up. And now we're going to actually be just looking strictly at graphs. We're not going to have a function in front of us. We're just going to be getting all of our information from the graph. So we want to determine whether it's a function by using the vertical line test. That's the method we use to see if something is a function. If it is, use the graph to find the following information. So first, if I'm looking at this passes the vertical line test. So I could describe the domain. We're going to, since there's no closed dots on the end, we're going to assume there's arrows. So the domain is all reals. And our range, if you notice, this graph is just kind of coming down, but never really going to cross the x-axis. So our range is y is greater than 0. Since it's never going to cross the x-axis, it will never have any x-intercepts. I have a y-intercept looking at this picture at y equals 1. And symmetry. When we talk about symmetry, we want to say, is it symmetric with the x-axis? The x-axis. Is it symmetric with the y-axis? Or is it possibly symmetric through the origin? So if we just look at this, I don't see any symmetry. Moving on to example 2. The domain of my function. The smallest x value I can plug into this function is -3. And assuming that would be an arrow there because there's no closed circle, this is going to go on and on and on forever. So it's -3 to infinity. Or we could just write x is greater than or equal to -3. Either answer is acceptable. You might feel more comfortable writing it in set notation, which is this guy over here. I may give you multiple choice where you have to recognize the interval notation. Our range. So our range is going to be our y values. And we look, our lowest y value is 0. but my graph is going to go on and on and on forever. So the range y is greater than or equal to 0. I have x-intercepts, or the graph touches the x-axis when at x equals -3, and also over here at 2. I have a y-intercept of 2, and once again, this graph does not appear to have any symmetry. The last function, oh, I didn't even, does pass the vertical line test. I didn't do that with the last one. Oops. My domain goes from -pi to pi. Or -pi less than or equal to x less than or equal to pi. Either way, again, is acceptable. My range, now I'm describing the set of y values, and if you look, my range goes from -1 to 1. I have x-intercepts at -pi/2 and pi/2. I have a y-intercept at 1. And this graph is symmetric. If you fold it on the y-axis there, you're going to have a mirror image. So it's symmetric with respect to the y-axis. Now let's get a little bit more in depth with how we're going to analyze these graphs. Okay. So now we want to compare function values to 0. So when we're dealing with functions, which variable, x or y, does the function notation f of x represent? And hopefully you're all thinking in your head, well, of course it represents the y value, right? We learned that in Algebra 2. If f of x equals 0 for a given point on a graph, then where is that point located? So if y is 0, hopefully you're thinking it's an x-intercept. If f of x is greater than 0 for a given point on the graph, then where is that point located? Well, this means if f of x is a positive number. So if you were going to graph the ordered pair -3, 2, you'd be going above the x-axis. If f of x is less than 0 for a given point, then where is that point located? And obviously, that would be below the x-axis. And this, hopefully, to all you guys, is common sense. We've just never really used the words like this before. So now we want to use a marker, a highlighter, or a colored pencil. Good thing we have our iPads. I'm going to use a highlighter. Trace the graph from left to right for any values on which the graph is. So we're going to do f of x equal to 0 first. Then we'll do f of x greater than 0. Then we'll do f of x less than 0. So we're going to start with where is f of x equal to 0? And obviously that's going to be at our x-intercepts. Identify the x values for the highlighted portion of the graph. So when x equals -3, 0, and 6. Now we want to talk about where the graph of f of x is greater than 0. So how do we show that? Greater than 0 is above, right? Ooh, you got to be careful there. Why do I have to be careful there? Because it's strictly greater than 0. So we really have to be careful because that at x equals 0, it doesn't really touch. So when we're describing our intervals, we're going to be real careful, and we're going to use parentheses. Because if you notice, this inequality sign is strictly greater than. So we're going to have -3 to 0, union 0 to 6. Now, if this had been greater than equal to, then we would have used brackets. If you prefer your solution set or set notation, and if you forget to put this little guy in there, I'm not going to make a big deal. Okay. Identify the x values for where the highlighted portion of the graph is less than 0. Okay, so now we're dealing with less than, and if we go, we're looking at this portion of the graph. So we want to describe that, and we want to be careful. So it's going to be, we start at -5 with a bracket because that point is included. And we go all the x values to -3, but don't include that. And then we're going to start at 6 with a parentheses and go to 7. And that's going to have a bracket. Once again, because that's included. So now, again, should your intervals identified above be identified as closed intervals or open intervals, and give a reason for your choice? Well, basically, they can be opened, closed, or a mixture, depending on what's being defined. Meaning, are we included or not? So we're going to be very aware of that and very, conscious of that when we're doing problems of this nature. And the last part of this example, we want to identify the domain of the graphed function. So our domain is going to be all of the x values that are being used. So if we look along the x-axis, the lowest x value I can use is -5. And since that's a closed circle, we get an answer for -5. And we go all the way up to 7. So I'm sort of trying to this year also transition you to interval notation whenever possible. But we can always rely on that set notation that we're used to. Identify the range. The range is going to go from the lowest y value, which is -4, to the highest y value of the graph, which is 4. And these are going to be with brackets because they're included, because our values are equal to it. Moving right along, getting a little bit more descriptive. Now we want to compare two functions to each other. Which variable, x or y, do the functions f of x and g of x represent? Remember, they represent our y values, right? They're our y's. If f of x equals g of x, what must be graphically true? So if our functions equal each other, that means they intersect. If f of x is greater than g of x, what must graphically be true? F is above g. If f of x is less than g of x, what must be graphically true? F is below g. And vice versa, depending on the situation and the way it's described. Now using these graphs below, let's see what we're doing here. We're going to use a marker or a highlighter. We're going to trace along the graph from right to left and then describe the intervals on which the graph f of x equals g of x, f of x is greater than g of x, or f of x is less than g of x. So I think yellow would be the easiest. So we want the x values. So we want to know where they're equal to each other. So where these two equal each other are going to be their points of intersection. I'm partially blind. They intersect here and here. So where do those intersection places occur? When x equals -2 and when x equals 5. In the next example, we want to identify the x values for the highlighted portion of the graph for which f of x is greater than g of x. So I just want to remind myself, f of x is the dashed line. So I want to know wherever the dashed line is above the solid line. There's my f of x is greater than g of x in those two portions of the graph. And that's going to be open parenthesis, because if you notice, when x equals -4, I have no answer there. It's an open circle. -4 to -2. That's also a parenthesis because of my inequality sign. Union, right? Also, and however you want to think about that. And from 5 to 7, but this time 7 is going to end with a bracket because there's a closed circle on my graph. Next, we want to talk about where f of x, or the dashed line, right? This is my dashed and solid. So where is the dashed line below the solid line? Dashed line below the solid line. And I can describe that as one large interval. And it's going to start at -2 and end at 5. And that's going to be parentheses because of our inequality sign in the beginning. The endpoints are not included. Now let's look at a weird type of question. Is f of 2 times g of 2 positive or negative? I don't care what the value is. I just want to know if it's positive or negative. So if I go to 2 and I look at f of x as a negative value, and I look at g of x, which is a positive value, if I was to multiply a negative times a positive, I'm going to get a negative answer. So it's negative. And again, don't even care about the numbers. Sometimes we do, sometimes we don't. Okay, I just wanted to know if it was negative or positive. Now we're going to use our little picture below. And we want to identify the intervals such that f of x times g of x is greater than 0. Before I move on here, this graph should extend. This graph does go all the way up. There's an arrow. Just so f of x times g of x greater than 0. So where is that going to happen? That's either going to happen where both graphs are positive or both graphs are negative. Since they're never negative together, I'm going to focus on where they're both above the x-axis. So they're both above the x-axis. Basically, that graph is above the x-axis there. And this graph is above there. So it's really the interval from 2 to 4. If you look at that, that's the interval where I'm going to have positive values. It's a little tricky. Where is f of x times g of x less than 0? Well, that's going to be when one's positive and one's negative. And that actually occurs if you look here from -2, right? That's going to go, I have a negative and I have a positive from -infinity to -2. And then, oh, it's easy to see here, 4 to infinity. Again, a little bit of a weird way to think of things, but very, very good to know for your future classes. And last thing we're going to do is a little evaluating. I'm going to try to get through all these questions. Some of them are a little wacky and they don't make much sense, but we will just try. Remember that if h of 3 equals 2, then that means when x equals 3, y equals 2. So we're going to find each of the following function values. So now we're going to evaluate from our graph. F of x is the dashed line, and g of x is our solid line. So if I want to, I might make f of x a highlight. That might help me a little more. What is f of -1? So when I plug in -1, I get 6. What is f of -9? If I go to plug in -9, I see I do not get an answer. That's an open circle. So f of -9 is undefined. f of 5. When I go to 5 on my x-axis and I go to 5, I get negative 5. G of negative 11. So I go over to negative 11. Remember, G is the non-highlighted, and that's negative 2. G of 7. I'm going to go to 7 on my x-axis. I'm going to go to the solid line, negative 1. It's a little hard to read. Now we're going to do some of our operations. So remember, f plus g of 3 really means f of 3 plus g of 3. So when I go to my graph, f of 3 is 6. G of 3 is negative 6. So my overall answer is 0. F of 3 minus G of 3. F of 3 was 6. G of 3 is, so minus negative 6 equals 12. G times f of negative 3. So I want G of negative 3 times f of negative 3. G of negative 3 is 2. F of negative 3 is 6. So our overall answer is 12. F divided by G of 2. So I want F of 2 divided by G of 2. Yeah, we might stop this soon because this is very repetitive. F of 2 is negative 3. G of 2, that was the weird one. This is the one I don't like. It looks like it's about 5.3, and I'm not even going to bother with that number. If you have a calculator, that's fine, but that's okay. The values of x such that f of x equals negative 3. So now we're looking on the graph where the yellow equals negative 3. So that's going to happen in two places. When x equals 2, and all the way over here when x equals 9. The values of x such that f of x equals 6. So I want all the x values that when I plug them in, I get 6. And if we look, they happen for a while here, right? This is an interval. It's not just one number. So we're going to describe that interval. And it's equal to, so we're going to use brackets from negative 6 to negative 1. The values of x such that g of x equals negative 6. Well, g of x never equals negative 6. It never goes down that low. If I trace along it, it never gets to negative 6. None. The values of x such that f of x is greater than 0. So I want to know where f of x is greater than 0, and the dotted line greater than 0 goes from negative 9 to 1. But we have to remember, negative 9 is not included because that was an open circle, and 1 is not included because of this inequality sign. And the values of x such that f of x equals g of x, what does that mean again? We're looking for where the graphs intersect. So if we go up to the graph and look for the two places where they intersect, not such great, you're going to have to estimate a little bit, but they're going to intersect here and here. And I would say that's approximately at x equals like negative 0.2, if you're approximating. And the other place was at x equals 9. Not going to worry about this right now. Last question. If p of x equals x squared plus 2x minus 13, for what values of x is p of x equal to g of negative 3? So p of x equal to g of negative 3. We're going to use our graph. G of negative 3 is 2. So we really want to set this equal to 2. And these are some things that you'll wind up doing in calculus, using a graph for one part of a problem and a function for the other. So we're just trying to get you in the habit of doing that. And basically, we could solve it quickly. Since it's a quadratic, we get everything to one side. And then you would factor. And your two solutions would be at x equals negative 5 and x equals 3. There you have it. A little bit of graphing stuff today. Practice, do your homework, and we will see you very, very soon. Thank you. Goodbye.